Welcome to Webinar Wednesday. We are glad to have you with us for today's presentation featuring expert Joni Charles, Ultrasound Modality Manager of Philips Multi-Vendor Services. Joni will aid engineers and biomeds in troubleshooting ultrasound image quality issues by providing practical knowledge, experience, and information. Webinar Wednesday would like to thank our sponsor, AllParts Medical. AllParts provides OEM replacement, Dunn, Lee, and Phillips parts from its 158,000 square foot facility in Nashville, Tennessee. In addition to part sales, AllParts has an extensive probe repair department capable of performing a multitude of repairs across virtually all probe types. AllParts also provides customers an extensive array of in-depth training classes and technical support before and after the sale. An ISO-certified quality management system helps deliver an industry-leading warranty rate for parts across multiple manufacturers and multiple modalities. For more information, please visit allpartsmedical.com. A few announcements before we get started. Don't miss our 20th anniversary celebration at MD Expo in Atlanta on April 11th through the 13th of this year. MD Expo strives to provide healthcare technology management professionals with a unique, intimate, and rewarding conference second to none. You can find all the details and registration at mdexposhow.com for details. As I mentioned earlier, our speaker today is Joni Charles. Joni, you may begin whenever you are ready.
Welcome. My name is Joni Charles. I am the Ultrasound Modality Manager here at Philips Multi-Vendor Services. Today's webinar is centered around troubleshooting ultrasound image quality issues. So without further ado, get started on the outline. So we will lay a foundation by starting with some fundamentals and physics of ultrasound and ultrasound machines and probes. We'll move into the formation or creation of an ultrasound image. We'll then talk about front-end architectures. After that, we will take a look at some appearance and aesthetics of a typical ultrasound imaging screen. Moving on from there, we will talk about different imaging modes. And once we've laid all that foundation, we'll talk about some of the inherent components of ultrasound image quality, some of the things that happen just because it's sound waves in general. After that, we'll jump into the troubleshooting section. That will last a while, and we will, at the end, conclude with some troubleshooting tools and talk a little bit about training. Ultrasound is defined as an oscillating sound pressure wave with a frequency range greater than the upper limit of the human hearing range, which is typically 20,000 hertz, putting their range in about the 2 megahertz to up to about 20 megahertz range. Every sound wave has 5 parameters to it, and those will be amplitude, wavelength, cycle, period, and frequency. And I only bring that up because we do talk about frequency a good bit here. These parameters work together to determine the depth, penetration, and image quality of a given transducer. For example, higher frequency probes have great resolution but are limited where penetration is concerned. Lower frequency probes can propagate further into the body, but their images are not as aesthetically pleasing because of their pixel size. Ultrasonic imaging is the non-destructive, meaning no harm done to the tissue or product, testing of structures and products. Ultrasound images are created by transmitting sound waves into the body and then interpreting the intensity of the reflected sound waves, which we also call echoes. Transmission and receipt are accomplished via a transducer or probe. The collected data is then processed inside the ultrasound unit and displayed in a black and white format called grayscale. Other aspects of the returning echoes, such as the phase shift and direction, can be processed for pulse wave and color flow imaging. So the most basic explanation of ultrasound would be in medical diagnostic ultrasound, images of soft tissue structures in the body are generated by transmitting sound waves into the body and then receiving and processing those reflected sound waves. As the ultrasound signal travels into the body, it encounters different acoustic impedances. These differences in acoustic impedance in the body are what cause the ultrasound signal to be reflected. These reflections, also called echoes, come back into the system and are processed and eventually displayed. By definition, a reflection is the return of all or part of the transmitted ultrasound signal. The reason why ultrasound cannot be used to image bone or lung material is because these structures have very high acoustic impedances and basically absorb or attenuate all the energy in the sound wave, leaving nothing to be reflected and processed. Every ultrasound transducer has what is referred to as a primary frequency, or F0, as depicted in the picture to your left. This is the optimum frequency of that particular probe. This frequency will provide the best overall image quality of all the available frequencies on this probe. The primary frequency sits at the center of the transducer's overall frequency bandwidth. What that means is that an ultrasound transducer can transmit and receive inside a range of frequencies, which you can see are F1 through F2, including F0, rather than just one single frequency. Often, the model name of the transducer will give you a good idea of what the frequency bandwidth is for that transducer. For example, a Philips L12-5 linear probe has a frequency range from 5 megahertz to 12 megahertz, making the center frequency of that probe 8.5 megahertz, which means that the best image quality you're going to get from that probe is at 8.5 megahertz. As the ultrasound pulse passes through a body, the tissue speeds up and slows down the signal slightly. The solid white arrows are the speeding up and the open arrows are the slowing down. This causes a distortion of the original wave and creates a second harmonic frequency. It actually creates multiple harmonic frequencies, but we're just going to focus on the second harmonic frequency for now. Harmonic frequencies are of a lesser amplitude, but they are normally less noisy or cleaner signals than the echoes at the primary frequency. So, they are amplified and displayed in a mode called harmonic imaging. How this is accomplished is by transmitting at the primary frequency and listening or receiving those echoes at the harmonic frequency. If you look at the picture in the top right of this slide, you'll see that in the example, they're transmitting at 3 megahertz, but they're listening at 6 megahertz for the harmonic. It's rare to encounter an ultrasound system that was manufactured in the last 10 years that does not have some kind of tissue harmonic imaging on it, and that's why I bring this up, is the background on a harmonic image is often darker than that of a primary frequency image, and I just want you to be aware of that when you start into troubleshooting. So now let's move to talking about the overall architecture of an ultrasound system. A typical ultrasound system will contain the following things: power subsystem, front end processor, back end processor, control panel or user interface, a display of some kind, software options and presets, and then a probe or probes. And all these things work together to create an ultrasound image, and we're going to look at these things individually as we move along. So we'll start at the top of that list and talk about the primary power supply components. They're typically primary and secondary power supply components. The list of components that would normally be found in the primary portion of the power subsystem would be a power cord, an AC input box or PCB assembly of some kind, normally containing a breaker switch, an EMI filter or a transformer, and some kind of internal cabling. And we kind of depicted that on the right-hand side here. These components are really all about getting the outside AC inside the machine, distributing it, and filtering out any interference that it possibly can. So in the secondary portion of your power supply, you normally find a main power supply of some kind, which can be a combination of AC and DC supplies that run the front end and back end portions of the system. There's normally some kind of transmit power supply or high voltage power supply that's the bias to create a strong ultrasound burst for the transmission into the body. And lastly, there's some kind of plus or minus 5, plus or minus 12 volt DC, and sometimes 3.3 volts DC power to run the hard drive, the DVD, the motherboard, and the back-end computer component. Newer systems often contain one main power supply that has all these components included, whereas older systems normally have power configurations that contain multiple power supplies. The portion of the machine that is referred to as the front end is that portion of the machine that does the work of timing, driving, and transmitting sound waves into the body, as well as receiving, processing, and storing the returning echo information so it can be sent to the back end of the unit for display. Typical front-end components would be some kind of probe interface board, TX and RX boards, or channel boards. There's basically two different kinds of front-end configurations, and we'll talk about that later. There's always some kind of analog to digital conversion because the echoes that are returned back to the system are analog echoes and have to be converted for display. There's always some kind of mid-processor or mid-processor board that strips off I and Q signal and does other things for different imaging, different parts of the image before it's sent to the back end for display. There is always some kind of front-end control board that helps to recognize the probe and set the front end up for running that particular probe. And also, it's typically the watchdog of the front end. It checks temperatures and voltages and things like that. And you can't talk about ultrasound without talking about the master clock and secondary timing. It takes an incredible amount of digital timing to transmit, receive, and display an image correctly. So if we pull the concept of a front end together and try to simplify it a little bit, we can think of the front end controller as a traffic cop, and it uses a system clock to make sure all the data is passed at the correct time. We have a probe plugged into a probe interface board of some kind. We have a transmit and a receive side. Whether they're on the same board or separate doesn't matter. System clocks are used on the front or on the transmit and the receive side to create an image, and that front end controller typically talks to the back end, which is the computer up in the top right hand corner, that has control over all of the system and also over the display of the ultrasound image. I mentioned before that there are basically two kinds of front ends you'll typically find in an ultrasound unit, and the first one we're going to talk about would be the TX-RX configuration. In this configuration, the transmit and receive functions of the front end are separated onto different PC board assemblies. And they normally have separate buses for the transmit and receive data. That's what you're looking at. The card cage to the right, you'll see those two green boards where the bottom side is facing out, and they are connecting between the transmit, the GRXs and the GTXs and the Gurley board. Those are bus boards. Some systems will have one transmit board and one receive board, while others will have multiple transmit and receive boards to accommodate 3D, 4D imaging and other advanced imaging capabilities. Along with these boards, it's necessary to have a beamformer PCB of some kind to handle the timing of the transmit and the receive signals. So that's what you see in this front end. What you're looking at on the right-hand side here is a Logic E9 card cage. The older style GFI configuration. There's a newer MRX configuration of this front end. But the systems that use this RX-TX sort of setup or architecture would be the older Acoustic Sequoia, the GE Logic E9, the Vivid E9, and there are quite a few other systems who use an RX-TX configuration. The other front-end configuration we want to look at would be the channel board or time delay configuration. In this architecture, the transmit, receive, and timing functions are all done on the same PC board. In this situation, there'll normally be multiples of this board in the front end. For example, a Philips IU22 has 4 channel boards in its front end, and a GE Logic 9 has 8 time delay boards in its front end. And what you're looking at here on the right-hand side is a Siemens S2000 card cage. It has 3 transmit receive boards. You see there on the left-hand side of the card cage, the TR0, TR1, and TR2. Those are identical boards that all do transmit, receive, and timing or summing delay is what we call it as well, in the front end. The other configuration that I'd like to talk about just briefly would be the compact portable configuration. With faster processors and more compact ultrasound units, the architecture has changed to be a more consolidated version of itself, where the entire front end of the unit is comprised of only 2 boards. One of those boards is normally the transducer interconnect board, and the other board handles all the functions of the front end. In the picture to the right, the PIR is the transducer interconnect board, and the VF64, the entire front end of the system. This system's a GE Voluson S6. It's one of the newer mid-range ultrasound units that GE offers, but they also use a similar design in the front end of the Voluson E10, which is a premium ultrasound. Let's move to talking about the back end of the ultrasound machine. The back end processor is that portion of the machine that is responsible for running the entire unit and making sure that the video and audio information is displayed in all the right places. The hard drive, SSD, the MO drive, and the CD/DVD drive are normally either a part of the back-end architecture or they are directly connected to and controlled by it. Different companies have different names for the back end of an ultrasound unit. It can be referred to as a back-end processor, or BEP in the GE world, the Unified Motherboard Assembly, or EMB, or UMB in the Philips world, or an EBOX, or an ATX unit. An ATX unit is what Samsung and Toshiba often call it. It can contain an off-the-shelf motherboard with an Intel processor of some kind. It normally, but does not always, contain at least one high-speed graphics card. The operating software, systems options, and presets are used by the back end to configure the system for the customer's desired use of the unit. It is responsible for the compression, storage, and display of the ultrasound images, and is also responsible for talking to the network and transferring images via DICOM. One of the most vital pieces of equipment where image formation is concerned would be the transducer itself. The ultrasound transducer is the bridge between the unit and the patient. Without it, there is no image at all. But we aren't going to dive into the architecture of the transducer because for this exercise, we're only going to determine whether it's part of the problem or not. Let's talk about software options and presets. Ultrasound machines are booted, controlled, and run by the software that is contained on their hard drive. And in today's world, most ultrasound systems are running with some combination of embedded Windows operating software and the manufacturer's own application software. On top of that, the options in an ultrasound machine are the licensed features that the manufacturer programs into the machine, including the serial number, that tell the machine what kind of machine it is, what probes it can run, what licensed software packages the customers purchase for their use. Then the presets are the customer programmable portion of the software. They normally contain the individual user-defined programs, patient demographic settings, setup for the calculation packages, and the network. Every ultrasound system has a control panel or a user interface of some kind. It's a console that allows the user to customize and control the system's operation. It normally contains system controls for gain and functions, an alphanumeric keyboard for entering patient data, touch panel for image control, and a trackball. Last but definitely not least, we'll talk about the fact that every ultrasound unit has its own display. Your display can be a CRT or an LCD. It can range in size from a few inches across to about 23 inches across. It can be integrated into the frame of the unit, or it can be mounted on the outside, like the one that you see to the right that is mounted on an articulating arm. So if we put all of the components that we've talked about, the major components of an ultrasound system, together into one unit, this is basically what we have. We have a power subsystem, a computer or back end, some imaging hardware, which is the front end, the probe that's the interface between the machine and the patient, and there's a user interface and monitor. We're going to switch it up now and talk about the typical imaging screen. And the reason I think this is important is because it's important to understand the different aspects of a typical ultrasound imaging screen and what portions of the system are involved in creating the data that you see in each of those sections. Like if we start on the left-hand side, well, first of all, let's qualify this by saying this is a GE Logic E10 ultrasound. On the left-hand side, boxed in hot pink, you'll see a few little images that I took and saved. And what you're going to see in this box as a tech does an ultrasound exam is the images that they are storing that are waiting to be processed in some way, whether sent to the network or saved on some kind of electronic media or just saved to the hard drive. Those will stay as long as that particular patient is active. Those images will stay on the screen with you. This particular part of the screen is generated by the software, the application software, and the back end of the ultrasound unit. If you slide down below that and look at what's boxed in gold, you're going to see the time and date, as well as network status, battery status, and quite a few other statuses. These are a function of your application software mixed with your OS software, which in this particular system is Windows 10, but also generated by the back end of the ultrasound unit. In other words, the back end processor, the ATX unit, the unified motherboard, however that particular manufacturer talks about the back end of their ultrasound units. And we are going to break that down very soon in this slide set. If we move to the top of the screen, the GE Healthcare logo, as well as the time and date again, the ADM that you see is how I'm logged in, and that's just a GE thing. You can be logged in as a user or as admin, and I log in as admin so that I can make changes to the software and to the settings if I'd like. The word test is the patient name in this case. Normally that would be a real patient name. If we slide over to the right, you'll see the model name of the probe and the preset. This yellow box is what we call the patient demographics. These are functions of the ultrasound application, so that means that they're part of the back end as well. If we take a look at what's boxed in blue, that is your actual 2D image. All of that is generated by what we call the front end of the ultrasound unit, the part that transmits, receives. It's a function also of the probe. If we slide to the right and look at the box, the vertical green box, you're going to see all the readout. Most of that is generated by the preset that you've chosen, but it's also all adjustable by the control panel. So these functions on the right-hand side are actually a function of front end and back end combined. And they're all typically adjustable by the control panel. So this is what a typical, what I call a no-image imaging screen looks like. This is what an imaging screen looks like with a probe plugged in and selected, but you're not actually scanning with it. Notice at the very top of each image contains some white ring down or side lobing noise. This is an inherent image artifact. It happens because the crystals in the probe expand and contract radially and create radial beams called side lobes. This is something that all ultrasound machines have circuitry to filter down to be as the least that they can possibly make it without taking away from the image. But it is not something that's wrong with the machine, and I just wanted to point that out before we start into the troubleshooting section. These are examples of normal black and white B mode images. Notice that there are many different levels of gray to depict different kinds of tissue in the body. Those different tissues have different impedances, and that's what causes the brighter or the less bright echoes. These are two pretty typical pulse wave Doppler images. All returning echoes contain phase shift and directional information. Pulse wave uses this information. It's also called the I and Q signal, along with a sample gate to create direction and velocity information to display on the screen. The picture on the left shows arterial Doppler, which is a carotid, And the picture on the right is a venous Doppler, which I believe is a hepatic vein. Color flow Doppler uses the exact same information as pulse wave Doppler does, but instead of assigning a level of gray, it assigns a color for velocity and a direction. Red is normally assigned to blood flowing in an artery, and blue is normally assigned to blood flowing in a vein. The last kind of imaging we're going to talk about would be what I call multidimensional imaging. This picture shows you the difference between 2D ultrasound, which are B mode ultrasound, and 3D 4D, as well as what's called HD live ultrasound, which is just in my mind, a souped up version of 3D 4D ultrasound. 3D 4D and HD imaging are all techniques used to create the illusion of depth by adding multiple slices of the image together. This requires some kind of specialty probe as well as some kind of motor control assembly to run them. And we're not going to get too deep into this. I just bring this up because anytime you have a machine that you're walking into that has the capability to do 3D, 4D, or HD ultrasound, you're going to have some specialty probes there as well as some added hardware on the inside of the machine. Let's transition now and talk about some image quality interferences. Because ultrasound is literally sound pressure waves, anything that wanders into its frequency bandwidth can affect it. The lack of a good ground in your power cord can wreak havoc on your image or your ability to send patient data over the network. The lack of fluid or dehydration can make it difficult to penetrate the body. The fact that there's no necessary shielding of the ultrasound scanning rooms leaves it wide open to stray sound waves. Radios, fans, light fixtures, phones, all of these things can affect the ultrasound image. Broken components inside the unit, like a failed capacitor, can beat off frequencies that the unit picks up and displays either in Doppler, color flow, or B-mode imaging. Patient movement or motion artifacts happen when a patient breathes, moves, or when you are imaging close to a moving structure like the heart. There are some normal imaging artifacts that you might come across as you are troubleshooting different kinds of ultrasound issues. The first one that we're going to take a look at would be the stitching artifact. That's that band that you see about 3/4 of the way down the 2D image is where the computer is overlapping the edges of each zone. That is a normal looking thing. You probably only ever see it on older systems, but it's not something wrong with the machine. It can be adjusted away with gain. And once you put an image up there, you don't see it at all. The second thing that we're going to look at is the absorption artifact. What you're looking at there is the larynx in a neck that has right and left lobes of the thyroid on either side, and then on either side there's also a carotid. What I want to bring your attention to is right behind the larynx, you'll see that big dead black spot. What that is complete absorption. And that's just an artifact that happens because there's bone in your larynx, and it absorbs all of the ultrasound signal, so there's nothing to see behind it because the signal is gone once it gets through that bony structure. The last one would be a wraparound artifact, and that is also something that you'll see when you do imaging. You'll see, even though you know you're at the edge of the dentum's walls, you'll see some ultrasound information outside those walls. In this picture, it's on the left and right, sort of at the bottom. That's just something that the computer and the ultrasound machine does. It's called interpolation or averaging. It actually puts things in spaces so there won't be blank spaces. And we call that wraparound artifact. So as we jump into troubleshooting, it's important to remember that the information in different parts of the imaging screen can be generated by different parts of the system, but they all have some common factors. For example, the LCD screen itself is fed by the back end of the system, but there's also a video cable that runs from the back end to the LCD display, and ultimately the video format is fed to that display by the back end, even though portions of it are created in the front end. So in light of that, the first question to ask in any image quality complaint would be, is the issue all over the screen? Because you want to verify that your monitor or LCD is functioning properly. And one of the ways that you can do that, especially if you've got one of the two top issues that you see on the screen, the dead monitor or the faulty monitor, would be to use an external monitor to just feed the video from the system or from the cable that's running to the monitor to an external monitor and verify that it's okay. And then you know you've got a faulty display or a dead display. And in the event of a dead-looking monitor or a blank-looking monitor, I would first check the power to the monitor before I went any further. Make sure that the power cable is seated in there tightly. Make sure there's actually the normal amount of power, whether it be a DC. A lot of these LCD displays are 24 volts DC or 18 volts DC. I would check that before I moved on to anything else. And then if your LCD display looks good, you need to work your way backwards through the video cables to the back end of the unit. And the first thing I check is to make sure that I've got a good graphics card. I will go to the back end of the unit and try to find a video out that works or that looks normal, like a normal imaging screen. Because the graphics card can fail. And the BEP is not dead, but the graphics card itself is failing. And if you look at a video that's coming off, say, the motherboard, it will look normal, but the one that's going to the monitor will not. The next thing you can look for is the actual function of the back-end processor, which in the third image here that says motherboard issue on it, that literally was a failed motherboard on a TX unit, where the system just boots up like this in a Windows, and this is like the Windows safe mode kind of situation, and you couldn't do anything. You couldn't move from there. Although I will say, in this situation, before I replaced anything at the back end, I would check to make sure that my hard drive and my software were working correctly. A lot of times in the GE world, reloading software on a GE ultrasound unit is used as a troubleshooting tool because there's so much failure in their software. And then the last thing I would say about this is before you order anything, monitor or install monitor or back-end processor, I would check the cabling between the back-end and the monitor. The reason for that would be that in today's world, most of those things are wired up through articulating arms, and they are moved and flexed and sometimes pinched inside that moving arm. And I can tell you that we've had multiple situations where we've ordered an LCD and sent it to an FSE, and it turns out he's got a bad monitor cable or a bad video cable or power cable to the monitor. So those are all things that you want to check if your issue is all over your screen. So the next question to ask would be, is the image quality issue in just the 2D or V-mode image? So when we know that the issue is limited to the actual ultrasound image, we can begin troubleshooting from that perspective. And the way that we get started with that is from the outside in. We ask the question, is the issue on all probes? And if the answer is no, meaning that it's only on one probe, the next step to take would be to move the probe to another active port. And if the problem moves with the probe and is only on one probe, you can safely assume that the probe's at fault. The next move to make would be to remove that suspect probe from the port and look at the connection pins and or the pinless grid, depending on what kind of probe it is. Check for broken pins or gel or other debris. Check the locking pin to make sure that it's mechanically and firmly locking into place. Inspect the nose piece of the probe, specifically for any gashes, cuts, cracks, or other damage. And when you've kind of settled on the idea that it's just the probe, that's your easy fix. You can call AllParts Medical and order a new probe. So if it's not clear that the probe is at fault, these are the next steps that you would take. If you move the probe to another port and the issue does not travel with the probe, you must then determine if the initial probe port is at fault. So what you do there, you would plug in another probe to that original port where you saw the issue, And my suggestion here would be to try to use a similar probe. So if you're seeing the issue on a linear probe, try to find another linear probe. And the same goes for a sector probe situation. And though I would like to point out, though, that often the port that the sonographer uses to switch to the TEE or the EVER probe, whatever special probe that they use, but they don't leave plugged into the machine all the time, this is the port that will exhibit wear and tear issues often. And if a port fails, it's normally one of these ports. So if the problem seems limited to just one transducer port, this could be a faulty transducer interconnect. So now let's take a look at how to troubleshoot an issue that's inside the machine. So what if the issue is on more than one probe and is exhibited no matter what port you plug the probe into? At this point, it's good to know what kind of front end you have in your unit. That's kind of why we went through the front end breakdowns ahead of time. Looking at the images to the right, the next question would be, is the problem in a section of the image or throughout the entire image? Asking this question can help you to determine whether you have a channel board or a receiver or transmit PCB or issue, or whether it could be in the front end control portion of the scanner. If you have diagnostics available to you, this is a good point to run them. Even if they are limited to just a pass-fail response without any details, a fail at this point helps you know that you're at least on the right track. So if you're troubleshooting an RX-TX configuration front end, and you have a system that has multiples of the same boards, like the one we're looking at here, the like boards can be swapped positionally to see what effect they may have on the issue in the image. Be careful to only swap like for like boards. For example, in this Logic E9, the GTXs and the DRXs can be swapped around positionally. However, the GRXs are normally two different boards, a GRX64 and a GRX128, and cannot be swapped. If you're able to move the issue by swapping the boards around, you've then narrowed your issue to a particular set of boards. You typically need only to order one of those boards to resolve your issue. And I will say in this configuration, this is a GE, and it's kind of hard to know what the part number on the board is. So if you need help finding correct part numbers, contact our in-house tech support engineer at AllParts. So if you're troubleshooting a channel board front-end configuration, the approach is similar. In the Siemens S2000 to the right, the TR0, TR1, and TR2 boards are identical and can be swapped positionally to see what effect that might have on your image quality problem. If moving the TR boards makes no difference, then you would next move to the RC board, which acts as the front-end controller in this unit. Because it sets up all the timing and control of the front end, it can also be at fault. I will say that on this particular system, you do have user-level diagnostics that you can use and will give enough detail that you will at least know where your problem, or at least generally where your problem lives. And the other thing I would like to point out is when you're swapping front-end boards around, make sure to do a visual inspection of each board, looking for some burnt components or broken components. Or the other thing is you want to check for seating anytime you have an image quality issue in your front end. Make sure that your boards are seated and the tabs are still working the way they're supposed to. But for more information on training on specific units, consult our website, www.allpartsmedical.com, because you can get specific training on this machine that would aid you in your ability to troubleshoot. Let's talk just a few minutes about pulse wave or continuous wave Doppler. That's just a different imaging mode in ultrasound. Often, but not always, when there are image quality issues in the 2D ultrasound image, there will be visible symptoms in other imaging modes as well. For instance, in the top left and bottom photos, there's a wiring issue in the transducer that causes spiky spectral information in the pulse wave and CW Doppler. In the top right picture, you can see a little bit of motor boating in the spectral image. This can be an internal or external noise issue. The reason I bring this up is anytime you are troubleshooting any kind of image quality problem, you want to look at all of your modes of imaging to see where and how often that problem shows up. same holds true for color flow imaging. In fact, the tech may notice an image quality issue in color before they notice it in the 2D image. The image at the top is commonly referred to as color spoking, and it is often related to a wiring issue with a probe. And wiggling the probe cable at the strain relief can make it come and go from the image. The image in the middle exhibits what's normally called color flash, and this can be caused by noise or motion or any other number of factors. The bottom image shows color bleeding outside the vessel. In many cases, this issue ends up being a PC board that performs the color signal processing on the receive side of the front end, or the memory that the color information is buffered in before being assigned to the color overlay on the screen. We cannot talk about troubleshooting without talking about ultrasound noise interference. Because of the natural physics of ultrasound, the systems and probes are vulnerable to pretty much any stray frequency that finds its way into their bandwidth. And some of the common culprits of this are like a radio, a fan, light fixtures, gel warmers, etc. Eliminating RFI, or radio frequency interference, or noise interference can be one of the most difficult things to accomplish because the machines are not designed to test for or filter out these kinds of interference. Let's take a few minutes and talk about how to troubleshoot ultrasound noise interference. Let me start by saying that the safest electrical configuration for any ultrasound unit is to be on a dedicated line. What this means is that the ultrasound machine is the only thing plugged into an outlet that is all alone on a breaker. Any other definition is not a valid definition of dedicated line. Practically speaking, though, it's rare to find this to be the case. We'll keep that in mind as we begin to troubleshoot any kind of noise in an image. So first you have to start with where's the noise, just in the image or all over the screen. This aids in determining whether the noise is coming, where the noise is coming from. Is it on all the probes? It's rare for RFI to be present on all probes. It normally exists in a specific frequency range, so it'll show up on one or two probes, but maybe not on all of them. Is it in one imaging mode, like color or Doppler or just the 2D image? This helps to eliminate some of the internal factors that could cause the noise. The next thing you want to ask is it at a specific frequency? If it occurs at only one frequency on a probe, it's probably external to the unit. When does it occur? Periodically or constantly? The reason I always ask this question is I have had several situations where when the noise is external to the system, it only happens at timed intervals, and figuring out what else is going on in the room while that interval is occurring helps you to figure out what's causing the noise to get interjected into your image. When did this start happening? Check to find out if any new electronics were installed around the same time. A new phone system that ties into that breaker can cause noise. There's so many other things that can cause noise that you want to walk into that room and just take a look around the room to see if there's anything there that you see that could be interfering with your ultrasound system. The following steps will aid in determining whether the noise is coming from the machine or something outside the machine. After asking the questions in the last slide, look around the room. Check to see what other electronic or electrical devices might be plugged into the outlets. And that's where I start. I start by turning off and unplugging any unnecessary electric devices, fans, radios, gel warmers, anything that you can see that is not necessary. I turn the lights off because every once in a while you'll get a fluorescent light that beats off a frequency in the 60 hertz range and it gets picked up by the power cord and carried into the system. If there's anything plugged into the unit, like a printer or a VCR, unplug it and remove it temporarily. Shut the system down and perform a physical check of the power cord and outlet. Are there any loose wires? Is the plug overly warm? Is the covering on the power cable beveled or twisted at all? These are all simple things that can allow noise into the ultrasound unit. If the noise issue is specific to a particular probe, unplug it from the unit. Check the pins in the connector for broken pins or dirt or gel or any other kind of debris. Check the strain relief on both ends of the probe. When the strain relief is worn out or broken, the cable is allowed to bend further than it was designed to, and the result is that the tiny wires inside the sheet break. Wiring issues are the most common cause of noise in the ultrasound image. They can be replicated while scanning by bending the probe at the strain relief to see if any smoking occurs in the 2D image. It also can be seen in color as well. And then the last thing, if you're able to do this, is move the machine to another room, another location, and plug it into a completely different outlet. If the noise travels with the system to the new site, then you've just eliminated pretty much everything in the original room as suspect. If it does not travel with the machine, then you know you've got something external to the machine that's causing your noise. If you end up in a situation where you find your noise is being generated from inside the unit, once it's been determined that the noise is coming from inside the unit, you want to make sure that there are no seating issues with the probes or any boards in the unit. In other words, make sure that they're seated properly. Sometimes reseating them helps. Number two would be begin troubleshooting in the same way that you would if you were troubleshooting an image quality issue. Most noise issues are related to something in the front end or in the power supply. And at this point, you may need some help, and our AllParts technical support can aid you in determining what the next steps would be for your specific. In many situations, one of the tools you're going to use in diagnosing an image quality issue would be the diagnostics that are on the system. Most systems have some kind of diagnostics available to you. Like in the top left corner of this slide, you'll see that's a GE, Logic E9, I believe. Common Service Desktop is what GE calls it. On the top right is a Samsung preset menu, and there are options for diagnostics in there. On the bottom left is a what they call a service user interface on an Accusson Sequoia. And on the bottom right is a Singo screen, which is the Siemens software that they use for maintenance. And there are diagnostics that you can run in there. A lot of these diagnostics are not the greatest of diagnostics, but any kind of help that you can get when you're troubleshooting an image is a good thing. The Alt-D logs on GE ultrasound equipment have turned out to be one of the most useful tools we've found in troubleshooting GE ultrasound equipment. We use them on a daily basis here at AllParts, and every GE training class that we offer here at AllParts comes with the instructions on how to access and analyze these logs. But it's a very simple process of just typing Alt and D on the QWERTY keyboard and choosing your destination and clicking on store, and then the system will store basically all of the logs that it is constantly populating to whatever media that you've chosen. Ultimately, every ultrasound system is different. The best way to equip yourself for troubleshooting would be to attend training classes specific to your systems. Here at AllParts, we offer training for the following manufacturers: GE, Siemens, Sonosite, Toshiba. So please consult the website for any information on training that you might need. So we've come to the end of this webinar. And ready now to move into a time of Q&A. I do appreciate you listening in and hope you've gained something from this.
All right. Thank you, Joni, for this valuable information. As a reminder to our audience, if you have a question for our presenter, please use the questions feature on the webinar dashboard. We do have a few questions that have come in already. I will go ahead and get started with those. Okay, our first question is, how have any of the major components in ultrasound machines changed over the years?
Well, basically, I've been in ultrasound now a little over 33 years, and they've changed absolutely dramatically over those years. But basically, they change with the changing technology. As processors have gotten faster and smaller, so have ultrasound machines. And a lot of times, we're talking a lot about the front end right now in this particular slide set. And I will tell you the introduction of the FPGA module really made it easy to make a much smaller front end.
Got it. And then we have another question that is asking where they can find a list of all of your ultrasound training courses available.
That would be on the website, the allpartsmedical.com, and then if you put /training, that should take you right to the page. And we do have multiple kinds of training. We have multiple modalities here at AllParts, so you would want to look for the ultrasound training.
Okay. And then we have another question that has come in. It is asking, what OEMs do you carry ultrasound for, and how would they be able to get a quote on parts or probes?
Okay, we carry multiple different OEMs. The biggest ones that we have would be like GE, Siemens, Sonosite, Toshiba, but we also carry parts for a lot of other of the smaller manufacturers. We have Samsung and quite a few others. But if you want to get a quote, you can do it one of two ways. You can email apmsales@philips.com, or you can dial 1-866-507-4793.
Perfect. That answered a lot of the questions that have come in. We have another. Someone is asking if they are a general biomed just breaking into ultrasound, what steps would you recommend them taking?
I would say we have a basic principles of ultrasound course. It's a 4 or 5 day course, depending on the number of people we get in that class. But it is an introduction. It's a deep introduction into ultrasound in general. And when you leave there, you'd be able to identify different kinds of ultrasound machines. You'd be able to perform a PM. You'd know what tools you needed. You would, yeah, that's basically it. But if you wanted, in any foundation, that's a foundational course. So beyond that, if you wanted manufacturer-specific training, that's when you would go to the website and say, hey, I need Toshiba. I have Toshiba in my hospital, or I have GE in my hospital. That's when you would look for the manufacturer model-specific training.
Okay, and it looks like we have time for one more question. We had someone ask if you could refresh on what manufacturers that you guys can provide repairs for the probes.
We do GE, Siemens. We do I think we do pretty much all of the TE manufacturers. We have quite an extensive group of those. GE and Siemens, Toshiba. I'm trying to think of those. We do not repair Sonosite probes yet. That's pretty much the three big ones are the ones that we do in general.
Okay.
Does that answer your question?
Yep. We had another person ask if you could review where the ultrasound training is listed on your site.
Oh, it is www.allpartsmedical.com and then /training.
Got it. Okay. That is all the questions we do have time for. I want to thank you again, Joni, for your time today and such a great presentation. I'd like to encourage everyone to visit today's sponsor to learn more about their services that they provide to our industry. Visit allpartsmedical.com. A quick reminder, you can obtain your CE certificate by completing the post-webinar survey. The survey will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit from the ACI, and you will be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. We will be back next week with another webinar. Visit webinarwednesday.live for more details and complimentary registration. Thank you.